Thanks everybody for being here today. I'm really excited to be here. Most of the time, I spend most of my time in Missouri, right? And to be just completely honest, there's not a lot of folks running these newer technologies in the state. I can probably count on one hand the guys that are really progressive and kind of pushing the envelope. And my guess is, or my perception, is that there's quite a few more of you in Ohio that maybe you're not running it, but you're at least interested in it. You've been exposed to it, and hopefully there's an interest in what I'm going to cover today. And the idea that I want to kind of keep with this talk is the idea of fusing this technology and agronomy. And I know I'm not the first one to say that. You've heard this bridging the gap, okay? We don't want to let that technology get too far out ahead of the science, right? And when we think about agronomy, that can be the soils, that can be the weather, that can be the genetics. That's kind of all wrapped up into one. And so we want to keep this in balance, right? And I would argue that as it sits today, that technology has probably advanced past the science, okay? There's some really neat things that we can do with a planter pass today, right? But do we have the sound agronomics or the sound science behind that to get the most out of that technology? And I would, like I said, argue that we're probably not there yet, but the work that we're trying to do is going to try to answer some of those questions and make us get the most out of it. And so it's no surprise, right? We know that the second we take the seed out of the bag and we place it in the ground, we're taking some off the top as far as yield potential. And so we know that planter pass is extremely important, and we want to preserve that as we go throughout the growing season. And if we screw that up and we do something wrong, okay, we're dealing with that the rest of the season. Okay, we can come back in with nitrogen and maybe rescue a crop, but we can't just make corn magically appear in the field, right? So we're really stuck with what we got a lot of times when it comes to that planter pass. And so we recognized this and wanted to kind of spend more time looking at the new planter technologies. And what you see running here is a Veris iScan. Show of hands, does anybody have one of these on a toolbar or a planter here today? Okay. Nobody? That's good, because this is the last I'm going to talk about it. But I just wanted to mention it because our research group, the USDA in Columbia, Missouri, has done a lot with Veris technologies, okay, soil EC and that sort of thing. And so that's kind of where we got our start. And this, we bought an iScan in late 2017, and we threw it on a little toolbar here. And that thing's measuring moisture, temperature. It's going to estimate organic matter, and it's also going to give us an EC value, okay. And so we wanted to start with that and see how could that information help us understand some things about like planter depth and residue management and that sort of thing. In the spring of 18, we started working with some growers, and we put some precision planting technology on a lot of our plot planters. Okay, so we're running 3 of them now, 2 4-rows, 1 6-row, and we're working with several different growers that range from 12 to 24-row planters in the state. Okay, and so in 2018, we kind of shifted to more of the commercial side of things and see, okay, what's actually on the planter, what's actually going across the fields today. And my guess is, whether or not you're familiar with Delta Force, you've probably, at least seen or heard about the hydraulic downforce, and you've probably also seen some advertisements for the smart firmers. And so, hopefully you're more familiar with this, and that's what I'm going to focus on today. So this research or this project that I've been working on covers a relatively large geography. This is a snapshot out of Climate Field View where you can see our different fields that we have data from. And you'll notice we go all the way out to Utah, okay? We've also got some fields here in Ohio. We're working with Dr. Alex Lindsay, and he's shared some of his data with us here from Ohio. So you can see we focus in Missouri, but we are trying to understand how these sensors are working across a wide range of environments. And so I'm going to focus most of my talk today on the smart firmers. Okay, I am going to bring in some as it pertains to the hydraulic downforce, but I'm going to focus mostly on the smart firmers. And I think this is a technology that really has the potential to fuse that agronomy and the technology. Okay, and again, I'm sure most of you are familiar with the smart firmers, but in case you're not, okay, it's a sensor that's going to replace our Keaton seed firmer, right? And we put an optical sensor on there. It's emitting 5 different wave bands of light, okay? And from the reflectance that comes back from those different wave bands, we're estimating several different soil properties. Okay, furrow moisture, organic matter, cation exchange capacity, clean furrow, okay, which is just the amount of residue in the trench, and then also furrow uniformity. And that's kind of a conglomerate of several of these metrics and just give us an idea of how even or how uniform is that seed trench. Okay. There's also a temperature sensor on it. I'm not going to get much into that today, but be aware that it also has that capability. So that's the Smart Firmer in a nutshell. And these things, I don't have a number as far as how many planters there are on in the U.S. or in the state, but they are getting used, and they're getting used to make on-the-go decisions. Okay? And so this is an article, the February edition of the Progressive Farmer. There's an article in there, a guy out in Colorado that's using organic matter to drive variable rate seeding and variable rate fertility real time. Okay? And so when I saw this, of course I kind of flocked to it and thought, well, I wonder if Brett here really fully understands what he's doing. And if he is, those decisions that he's making real time on the go, are they sound and are they the best for his operation? And so I want you guys to keep that in mind, that realize this idea of using these sensors to change inputs on the go is being applied to at least some acres in the United States. And so our goal as researchers was first to just see, do these things work? Okay? If we're going to rely on a sensor to vary our seeding rate or change hybrid on the go, we better have some confidence in it, right? And so if we get an organic matter reading from the cab, how is that relating to a soil sample? Okay? So that's just an example there. That's the first one. We want to have confidence in the sensor. The second is going to be our in-cab diagnostics. Okay? Is there something actionable from this information that'll make me stop, get out of the cab, make an adjustment, okay, and be better off from it? And so we're going to think about that as kind of during the planter pass in the field. And we want to see, does that give us an insight or a window into how even our corn is coming up, or at least the final stand at the end of the year? Okay, and that's kind of the way we're going to evaluate that. The next one, or the final one, is going to be yield potential. Okay, because if we're varying those inputs again on the go, the idea there is we're trying to get a window into the yield potential of our soil. So does that seed zone, okay, does that upper 2.5 inches, is that a surrogate for predicting the yield potential of a soil? Can we do that? And that's kind of what I'm going to cover here today. Okay, so we can kind of keep that in the back of your mind. Again, I'm going to start with the sensor performance. Okay, there's two things I want to cover here. One is the accuracy. Again, if I take a soil sample and I sense the same part of the field, how do they relate? Okay? The second side of this, the other side of this coin, is can I plant the field twice in a week and get the same map? Okay? Is it consistent? Is it repeatable? And so I'm going to start with the accuracy. Okay? We've done a lot of this. From Utah to Ohio. I'm going to just show you a case study from central Missouri. This is a river bottom soil, a farmer we're working with. It's got over 500 acres of grid soil sampling data. Okay? And that's the organic matter map from the planter that you see there, and there's all our grid soil sampling points. Okay? So now we can go out and see how did they relate. And I've zoomed in on one field here, okay? This is about a 120 acre field. And it's the most variable field in this river bottom that we did work on. Okay? So it's a prime candidate to see how accurate is the sensor. And you'll see with the Smart Firmer organic matter on the left and our grid soil sample organic matter on the right, you can see there's some similar spatial trends, right? The spatial structure looks similar. Okay? But if we focus in like on the southern half here, okay, where we've got, this is a lighter, sandier texture, okay? The organic matter went down in both cases, but what you'll see is that the Smart Firmer was overestimating the actual grid soil sample. Okay? So these readings were between 2 and 2.8. This was between 1.3 and 2. Okay? So we're almost doubling the actual measured organic matter. And if we look at the raw data, you can see that kind of in graphical form here. Okay? So on the y-axis, we've got our Smart Firmer estimated organic matter. And on the x-axis, we've got the lab measured, that LOI test. We sent it off to the lab and saw how they related. Okay? This line dissecting the graph here is our 1-to-1 line. In a perfect world, they'd all fall right on that line. Okay? If they're above it, it's an overestimation. and if they're below it, it's an underestimation. Okay? So what you can see here, again, I'll just reiterate, is generally overestimating our organic matter. The other thing that I'll highlight is that slope, if we go to this regression equation here, is 0.5. Okay? We would want that to be 1. So basically what we can say here is that we are detecting changes in organic matter, but we're not capturing the full range. Okay? And why this is because we're trying to apply a global algorithm to predict soil organic matter. Okay? There is no field calibration, there's no field-specific soil sample that helps adjust these readings. We're trying to use one algorithm to apply everywhere. Okay? So this is kind of what we're stuck with, if you will. It's still promising that we can see it's detecting differences, but just realize it's not perfect. Okay? The next thing I'll show you is the CEC, because those are the two big ones, right? It's hard to do this with moisture or residue, because that's going to change year to year. But our organic matter and our cation exchange capacity should be fairly consistent. Okay? And so you'll see a similar response in the CEC. But what I want to just highlight to you guys, if you are running these, their algorithm is going to change for 2020. Okay? So your CEC maps from 2019 are not going to look like 2020. So I'm not going to spend a lot of time on this, but I just wanted to at least illustrate that to you. And we learned that because when we looked at 2018 to 2019 organic matter, the maps look completely different. Okay? And so we talked to their engineers and they told us, well, it's just an algorithm change. Okay? So going forward, organic matter should be similar, all right? But the CEC is going to change. So that kind of just is an illustration of the accuracy. And again, I could show you a lot of data from multiple sites, but this is kind of the trend that we're seeing no matter where we go. Okay? The next thing I want to talk about that I mentioned was the repeatability. Okay? If we plant the same field 2 or 3 times in a season, how consistent is it going to be? And so we went down to a different river bottom field here. You can see me in there planting. And this is actually the east side of the field, you'll see we've got a real light sand. On the west side, we've got a heavy clay texture. Okay, so within a very small 10 to 15 acres, we're getting a wide range in soil texture. So this is a perfect place to go test this. Okay? And unfortunately, like I'm sure a lot of you dealt with in 2019, we had a ton of prevent plant acres in Missouri, right? And so we actually went down and did this in September of 2019 and took advantage of some of those flooded acres. And that's just to illustrate, to kind of get in your mind the soil textural differences across this site. So here's week 1. Okay? Left side of the field, you can see a higher organic matter where we've got a heavier texture. The lighter sand, we had a lower organic matter, kind of what we'd expect. Okay? Here's week 2. Alright, does that look the same? No. Here's week 3. Kind of a mix of the two. Okay? We had rain between each of these, which made it interesting. Okay? We had about 6/10 between week 1 and week 2. We had a couple tenths between week 2 and week 3. Alright? So there's the moisture maps, so you can kind of get an idea of how that moisture changed from week to week. What you'll notice if you look at week 2 here, you see this zone in the middle? Okay, and it is kind of washed out, and I apologize, it's hard to see. But that's dark green right here, okay? So basically, where that moisture increased, the sensor was estimating a lower organic matter. And that's, I think, I don't know this 100%, and I can't totally confirm this, but their algorithm is trying to account for moisture, right? If a dark soil, we've got to be able to differentiate, is that because it's higher in organic matter or because it has more moisture? And so when that moisture level went up, then our organic matter went down. Okay? So the stability of the organic matter is something to just kind of keep in the back of your mind. Alright? I'm not going to say this is going to happen on every field that you plant, but this did happen in our repeatability test. So as the environment changes, it could potentially change the readings that you're getting. Okay? So now, I don't want that to come across as too negative. Okay? Because I still think there's a lot of potential here. And if we think about the density and the resolution that we're collecting data, if we think about a traditional soil sample, we're collecting, less than half a point or half an observation per acre, right? We compare that to a planter pass, Okay, now we've got organic matter on the planter pass. We're collecting 125 points per acre roughly. Alright, now with some new technology, we're getting that information row by row. Okay, so now the number of observations that we get from a planter pass are extremely, extremely dense. And there's a lot of information that can be gleaned from this. We just have to, as researchers and in our field, understand what can we do with all of this information, because there's a lot of data here. Okay? And so, what I'm going to move to now is how can we use it? Okay? So now that we kind of understand how it's going to perform and how it's going to change, we want to see how can we use it. So before I switch gears, are there any questions as far as the repeatability or the accuracy of the sensors? Yeah.
Just one. I mean, what is being measured, or what's the depth of measurement of the seed kernel versus taking material aided soil samples?
That's a perfect question. Absolutely. You're looking at different depths, right? And so we've done this where we've taken, yeah. Oh yeah. All right, thanks, Harold. So his question was, I'm comparing a 6-inch sample to, a 2-inch, right? That sensor can't look down at 6 inches. Okay? So that's part of the overestimation, especially in a no-tilled field. We have done this where we've taken just 0 to 2 and then 2 to 6-inch samples and seen, okay, how does that compare? And basically what we see is that the regression curve, okay, is still not 1. That may shift the line down closer to the 1-to-1, okay, but the response is still not there. So that's a great question and a great point, and one that I actually wanted to make and I skipped over. So you have to understand that the depth that we're sensing, we got to make sure we're measuring at the same depth. Okay, so that's a great question. Any others? Okay, well, if anything comes up, raise your hand, shout it out, and stop me as I go through here. Okay, so when we think about the Cab Diagnostics, all right, what are the two main things we're going to focus on there? Okay, in my mind, it's depth and residue management. All right, and again, what's actionable? We're getting information about moisture, okay, that can hopefully make us make a better decision on planting depth. And we're also getting that furrow cleanliness, that furrow uniformity measurement to kind of give us a window into our seed to soil contact. Okay, so we're getting some information there. Can we use it? Now I'm going to show you some figures here, and they're basically looking at the frequency or the number of observations that we saw relative to the clean furrow measurement. Okay, at different planting depths. So this distribution in the red here is our shallowest planting depth. Distribution in the green is our deepest. Okay? This dashed line here illustrates the average. So what we can see is as we go deeper, okay, our clean furrow measurement is increasing. So when we think about, how many guys in here are no-tillers? Few of you. How many of you are using cover crops? Okay, several of you. This is what we're seeing, okay? When we think about, when you go out to make a depth decision, all right, in a no-till field, especially a no-till field with cover crops, can we base that on moisture? One guy in the back shaking his head no, and I'd agree with him. Okay? What we see, especially when we try to push corn early in an environment where we're no-tilling, we have cover crops, it's wet. Okay? It's always wet. So if we invest in a technology like smart depth or something that's going to change the depth on the go, and we try to use moisture, okay, we're just going to be planting at the shallowest depth that we're going to allow the equipment to plant at. Okay? It's just going to be pinned. But what we'll see here, okay, is as we go a little deeper, we can improve the environment that seed is being placed in. Okay? We're getting out of that residue. And maybe you guys already know this, okay? But in my mind, a lot of people I talk to, especially in those rougher conditions, they want it shallow because they want it to get out of the ground. But in actuality, if we went a little deeper, okay, again, we could be placing that seed in a better environment. And that's just residue, okay? And what you'll notice is that these bell curves here are about the same shape as we transition between depths. But what about when we look at the overall uniformity of that trench? Okay? Now what we see, especially here at the shallow depth, we get a wide bell curve. Okay? So what that means is we have a very inconsistent seed trench environment at a shallow planting depth. And we go a little deeper, it's much more consistent. Okay? So we're getting better seed to soil contact. We're not getting voids in the trench. Whatever it may be, there's not as many inconsistencies in moisture. So we're just placing that seed in a better environment. So this is kind of just one thing that we just noticed. We weren't setting out to answer this question, but it was just kind of a byproduct of some of the depth trials that we were looking at. Okay? So moving from kind of that depth idea, taking that a step further. You guys have probably heard the term emergence window or the concept, okay? And so basically how we define the emergence window of a corn crop is when 10% of the plants are emerged, that's day one, okay? Until we've reached 90% emergence, okay? And that time from day 1 to 90% is our emergence window, okay? So what do we want our emergence window to be? 1, 2, 3, 1 day, right? We want them up as consistently as we possibly can. We want that number to be small. And here's where I'm going to show you some of Dr. Lindsay's data from Ohio, okay? And this is from his planter depth study. And what we see here on the x-axis is our smart firmer moisture. Or on the y-axis, I'm sorry, is the smart firmer moisture. On the x-axis is our emergence window, okay? And what you'll see is that there's a stark contrast. We can draw a line across there at 40%. Okay? So if we had a smart firmer moisture of at least 40%, our emergence window was generally between 2 and 3 days. Okay? That's as good as we could get. So this tells us that if we'd have been using that smart firmer metric to guide planting depth, in theory we could have improved our emergence window across this site. Okay? Now, one thing I'll point out to you is if you read the literature on this, it would tell you 30% is all you need. Okay, so under this environment, this year, 30% wasn't enough. Okay? 40 was where we needed to be to get into that short emergence window. Okay? So we've kind of covered how residue and depth interact, and now we're looking at how moisture, depth, and the emergence window all interact. Okay? So trying to get at those NCAB decisions. Any questions on that? How deep are your no-tillers planting your corn? 2 inches, Harold says. Any others? Okay. So again, just keep in mind, don't be afraid to go a little deeper. Okay. Especially if you're incorporating cover crops into that rotation. Now, when we think about the data that I just showed you, okay, with emergence window, we're generally looking at emergence or population in a point measurement. Okay. We're planting a field. We're going back out. I've just done a little illustration here where we've got these pins. We went out and we looked at what was the stand, what was the emergence window there. And that's interesting. Okay, and we can definitely learn something from that. But where we can take that a step further is where we can now utilize that row by row information, okay, that we're collecting from the planter, and we can combine that with what we refer to as our stock counter data. Okay? From this, we've got stock counters on our combine's corn head. Okay? And so it's basically just a spring-loaded rod that detects each stalk as we harvest the corn. Okay? As that rod releases the stalk, there's a sharp drop in voltage. Okay? And so we can actually calculate based off the position of the combine and in reference to where our row units are on the machine, we can actually georeference each plant in a field. Okay? Now there's going to be some error associated with that with our receivers and that sort of thing and with the math that goes into it. But we can start to get a spatial coverage map of our actual final stand. Okay? And when compared to what Dr. Fulton and you all are doing out here at Ohio State, we don't have a lot to brag about when it comes to precision ag research. Okay? But this is one thing I can bring you from Missouri that maybe you haven't seen before. Okay? And it's kind of unique in that sense. And so we went out and tested this, okay, at our research farm, And what's unique about this site, okay, is all these corn plots you see here, we've got different cropping systems. We've got tilled plots, no-tilled plots, and no-till with cover. So we've got different cropping systems, and they're located across a landscape. So we get the soil variability to kind of look at as well. Okay? And so you can see here how we've got a no-till versus a tilled corn, and then we've got our different landscapes associated across there. So it's a neat place to kind of evaluate the planter sensors with that and use that in conjunction with our stock counters at the end of the season. Okay? So if we get back to the frequency graphs, hopefully you guys are kind of up to speed on what to look at here, but now our colors have changed. I'm not looking at planting depth. I'm looking at cropping system. Okay? And what we found was that when we look at our stock counter data, okay, what had the lowest average population? No surprise, our no-till with cover crops. Okay, it was hard to get a stand there. If we look at the no-till versus the tilled, okay, the average is pretty similar. But what did I say about that distribution? Okay, in the tilled, that red curve is spread out. Okay, so we had more variability in the tilled as opposed to the no-tilled. Okay, so that's how the population landed between our cropping systems. But now we can kind of try to drill down a little more and say, okay, why? And could we have used the planter to either adjust something on the go or at least understand why these differences changed? Okay? So now I'm going to look at the planter data. And this broke out pretty interestingly. Okay? Our no-till was the driest. Okay? We've got smart firmer moisture across our x-axis. The tilled was somewhere in the middle, but what you'll see is this high peak. Okay? There was not a lot of variability in the tillage. Okay? We had overcame our moisture variation by tilling this field. Alright? And then on the high end, again, no surprise, our no-till with cover crops, it was just plain wet. Okay? So we see, alright, moisture potentially could explain some of this, but let's go a little deeper and let's see what else can we answer from this. And this is where these stock counters really get neat. Okay, I'm going to show you a few of these graphs. This one's just an example. Okay, so get everybody on the same page. But across the x-axis now, I've got plant spacing. Okay, and on the y-axis we're sticking with frequency. So this big curve you see here, okay, that's our target spacing. We want that peak to be high. That means every time there was supposed to be a plant, it was there. Okay? This next curve here is a single skip. So if there was supposed to be one, it wasn't there, but our next plant in line was there, okay? Now we're going to get a hump there. And then way out here, we've got our double skips. Okay, so we can look at how did our spatial variation of skips occur across these different cropping systems, across these different soils. Okay, so it's really kind of a unique and interesting evaluation. I skipped over the doubles. Our planters today, our singulation's pretty good, our spacing. We don't get a big rise here, but we do have the ability to detect those doubles as well. Okay, so we kind of got 4 different things here. But again, this is our perfect curve. We'd love to have no hump out here at a single or a double skip. Okay? So now let's look at moisture. Across everything, how did it shake out? Well, the green was our low moisture. And basically what you can see, the peak of that curve, okay, is higher in a low moisture versus the high moisture. Okay, I've just bend the moisture levels to say, was it above 40 or was it below 40? Because a lot of the data that we've collected up to this point told us we wanted to be above 40. Okay? What happened in Missouri in 2019? The exact opposite. Okay? So moisture still gave us a window into stand, but it was the exact opposite response that we saw, like what I showed you with the Ohio data, as well as some of the stuff we'd done in 2018. Okay? So these frequency graphs, these skips and doubles, does that make sense to everybody? If you got a question, just shout it out at me here. But let's take that a little bit further. Okay? we know furrow quality should be kind of giving us a window into this too, right? And so I binned it. Was our furrow quality at 90, 95, or between 95 and 100? Okay? Basically what we could see is that when our furrow quality dropped below 90%, we had a penalty in our stand. Okay, so if we could keep that above 90, we were okay. But once we fell below that, alright, we ran into problems. And my guess is, or my gut, that this may be a little bit better metric to kind of use or to guide from the cab, because these moisture variations, it's going to depend on what happens after planting, right? So if I had 40% moisture at planting like I did in 2019, and then we get 3 inches of rain the next day, okay, that's going to be bad, because now I put it into a wet soil and we got more moisture. Whereas we looked at like Ohio, and I didn't mention this, but that corn was planted in June, right? So we're trending drier. So now it's going to depend on where we're at, what the forecast is, and that sort of thing. But this furrow quality, if we've got residue, we've got inconsistencies, okay, that's probably going to be a technique to hopefully predict the stand that we're going to get regardless of how much rain we get after we plant. Okay? So that's kind of looking at moisture and the furrow uniformity. Now, I'm just going to briefly touch on this, but as I already mentioned, and as you already know, we're collecting a ton of information with one pass, right? And what I've shown you so far is just looking at one variable, right? Does moisture affect stand? Does furrow quality affect stand? But what about if we could look at all those together and try to make some more informed decisions, okay? And that's where this machine learning or statistical learning comes into play. Okay, and it's basically going to take all of these different layers of data, okay, look at it all together and see how can we predict final stand using advanced techniques. All right, and one kind of unique way or thing that we can look at is a decision tree. Okay, that's one method from this machine learning that's kind of unique. And basically what this does is it kind of takes you through different steps. Okay? So my first cut here is at 41%, real close to that 40 that I've been talking about. Okay? That explained the most variability in stand across our site. That's our biggest split. Let's say our moisture was above 41%. Okay? We're on this side of the curve, this side of the tree. And we were carrying a lot of weight on the gauge wheel. So our smart farmer said it was wet, and we were compacting that seed trench. Okay? That's the worst stand we got. So now we can kind of look at these different layers that we're collecting and kind of make some decisions. Okay? Now let's say it was wet, but our downforce wasn't too heavy. Okay? We weren't carrying too much weight on that gauge wheel. Now we can pull in furrow quality. Okay? And whether or not it was above or below 92% helped us understand what that final stand was. Okay? So you can kind of work through these and understand how these different things are interacting. On the right side of the tree, let's say we were less than 41, and now we're less than 39. Okay, you can kind of step through this, but basically all this is saying out here, our best stand was where it was dry. Okay? So I just want to kind of introduce this to you guys. Okay? It's tough to really take this home and apply it directly without kind of understanding how this works, but just know this is where things are going. And maybe in the future we're going to have a metric in the cab, okay, that can be a combination of these different things to help you make a more informed decision, okay, to try to use some of the newer statistical techniques. Now what I'm going to kind of finish up on or conclude with is going to be our yield, okay, and that's, my guess is probably hopefully what most of you were interested in, right? How do these metrics relate to the yield that we get at the end of the season? And I'm going to highlight organic matter. Why? So we remember back to Brett at the beginning of the talk, okay? He's using that OM to guide those decisions, okay? Is that sound? Can we back that up? And I'm going to show you some data that's just pulled out of a transect, okay? Usually when we look at these, the spatial data, we're looking at it from overhead, right? From a nadir view. But now we're going to kind of piece that out and look at it. What's that look like from the side? Okay, how does that look as we go down slope, as we go across the landscape? How is that organic matter changing? How is our yield, what's the function of yield and response? Okay, so we planted down the slope. Alright, there's our organic matter. Okay, it followed a real nice trend. We could see as we went down slope, that organic matter went from about 1.5 to 2.8. Okay, so in 600 feet, that's my distance down here, we had a pretty large variation. Okay, now the question is, how about yield? Okay, if we're using OM, what would we want this to look like to guide decisions? Would it follow suit? Is that what we'd hope? Yes? No? What do you think? Typically, what's our higher producing soil? Higher organic matter, right? Exactly. So that's what we'd shoot for. This is what we found.
It was a wet year.
It was a wet year. Okay. That definitely comes into play. But these soils, I haven't shown it to you, this is an eroded backslope. Okay? It's always low producing. And this is saying, I've got a higher organic matter on that eroded backslope. Okay? Couple things I want you to take from this. One is, that's a pretty darn good relationship. Okay? I don't have the regression equation up here, but you could kind of picture it. Okay? As that organic matter went up, our yield was going down, and it was following in agronomy, it's tough to get relationships that good. Okay? So this was exciting to see, but just understand that it's exactly opposite of how it's being marketed. Okay? And so we have to understand that when we're collecting this data, there's a ton of value in it, but it's going to be soil specific, it's going to be region specific, and we have to understand how it's acting on our field and our soil to make an informed decision. Because I would argue that we could probably make a pretty darn good decision with this if we wanted to vary our inputs. But if we'd have just shot from the hip right out of the gate and said higher OM is our higher yield potential, okay, we wouldn't have came out ahead at the end of the year, I can tell you that. Right? So that's kind of what I wanted to illustrate to you there was that there's definitely some great information to be gleaned from this, but we've got to interpret it with a little bit of caution. We need to take a step back and see how it's going to act on our field. To bring in the machine learning concept one more final time, okay? Right now, it's kind of being marketed as we're going to use OM, we're going to use CEC to make that decision. But where potentially this could lead to is using a combination of metrics, okay? Let's use all this together to try to come up with, at least in my mind, a productivity index, okay? Instead of just saying because my organic matter is higher, I've got higher yield potential, okay? Let's use several of these, come up with a yield index or some sort of index that helps us kind of make a better, more informed decision. And we can kind of use machine learning to understand that, okay, this is a variable importance plot. And basically all it's going to tell us is when we put all these different metrics into a model and we try to predict yield, how important each one is. Okay? And so we can kind of, as researchers, start to look at this and see as we change environments, what's important on this soil versus this soil, and kind of put all that together to see, what's most useful for you in the environment that you're on. So I think where this may go in the future is instead of just thinking higher OM is higher yield, we may need to take a step back and think how can we come up with management zones or some type of productivity indices to see how that's going to actually impact the final yield potential on our soils. Okay? So just to wrap things up here. All right? If we think back to the performance, okay? It did all right with accuracy, but that OM estimation from week to week, like I showed you, was a little bit inconsistent. Okay? If we think about the Cab Diagnostics, that moisture and the uniform furrow and furrow quality are all metrics that we can use to make an informed decision. Okay? But, for instance, our moisture is going to be year and soil specific. Okay? And then lastly, with that yield potential, it's going to relate, in a lot of cases, not all, but in a lot of cases, to that final yield. But the final relationship is probably going to be soil specific. Okay? And so with that, again, I really appreciate you guys allowing me to come out here and talk to you, and I'd love to entertain any questions that you have for me. Yep.
Why don't you have any nutrients as part of this? Is that just because you have the sensors?
As far as seeing how it, so the question was about nutrients.
Yeah, phosphorus, potassium, nitrogen.
Yeah, absolutely. So we have fertility data, obviously, associated with a lot of this. I haven't really dove in to see how do those relate. I know in certain circumstances it would, like if we think back to this figure here, at these different landscape positions, we could probably use this to, like the organic matter estimation would have related to soil test phosphorus. As you move downslope, that phosphorus is going to hang with that soil. Okay, so we've got high soil test phosphorus at the bottom of the slope. So there are relationships there. I just haven't really dove into it. I've focused more on yield and stand is what I've focused mostly on, but good question.
Question on that. Did you compare the smart farmer data to your EC data
Yeah.
relative to the maps it makes?
Absolutely. So yes, we did. So obviously, we've done a lot of EC work. So that was one of the first questions we wanted to see. And in a lot of cases, that moisture was a good indication. Okay. If you think back to that repeatability field I showed you with the sand and the clay, the EC was identical. Where we had low moisture, it was sand. Okay. We had a low EC. And that's where, I think we can kind of start to put pieces together. Okay. So there are certain metrics that are going to relate to EC. Okay? If we can show that and be confident in it, if we get a moisture metric and so we're understanding the moisture at planting and we can relate that to EC or soil texture, okay, that could be a really good tool to come up with a nitrogen recommendation. And so it's something that I didn't really hit on. But there are certain cases where these sensors are relating to soil texture. And one of the big ones that sticks out in my mind is, remember these things are detecting voids in the soil. Okay? What happens when we till a wet clay soil? Clods, right? Big nasty clods. That sensor's going to see it. Okay? And so if we till, especially when it's wet, and then we plant, we can get a map that looks pretty darn close to our soil texture, okay, by the management that we've kind of influenced on that soil. So when we start to put all those different things together, there's a lot of untapped things that I didn't cover today that we're looking at and that you can keep in the back of your mind. That kind of answer your question there. Other questions, guys? Anybody using these? Yeah.
I noticed on your chart, the thing I noticed most was it was kind of a disadvantage for cover crop.
Like with the population? Yeah. So that's that's always the struggle, is getting that stand and that cover, right? And that's kind of, it's going to be, I'll say that data, okay, it was just too wet. We should not have been planting. The no-till, just the straight no-till, and the tilled was okay. But it was just way too muddy in that cover crop environment. And I think we're going to have to understand, how can we manage the planter? For instance, okay, we started with row cleaners, trying to plant into that stuff. I don't know if anybody's tried that. You plant into 6-foot tall cereal rye with row cleaners. It doesn't work so well. You throw spike closers on the back, and you really got a mess. Okay? But what we're starting to look at is just actually taking those completely off and running brand new seed openers, okay? And that's where we can use those furrow quality measurements to see, okay, maybe I can take my row cleaners off, but I need to go a little deeper to get into a get good seed to soil contact in that high residue environment. So we can start using these to make us better managers of those cover crops and of the seeding pass.
What was the cover crop then?
Yeah.
What long?
So some of it was, depending on, the data I showed you there was a cover planted after wheat. So it was like the worst case possible, right? You got your wheat straw, we planted cover, it all died over the winter, we had this heavy mat, we also had some cool seasons in there, cool season cereals that made it up, so we did have some green material. It was not the ideal environment. We also planted into 6-foot tall cereal rye, planted corn, which you're not supposed to do into cereal rye. But when we pushed that into June, we found actually that field that I showed you, where I showed the stalk counter versus the planter pass, that was planted in June in a 6-foot tall cereal rye. And again, we could use that furrow quality measurement to kind of guide our planting depth and make sure we were getting good seed to soil contact, and that was the best corn on the farm.
See, I don't plant cover crops, and I figured to learn more about it, and mine would probably end up like this.
Exactly, yeah. That's everybody's fear, right? And so, I know this isn't a cover crop talk, but we have done a lot of work with it. And so I'd recommend with starting small and starting with a late planted cover. Okay, and maybe that makes a few of you in here cringe, but if we can plant a cereal late, okay, it's not overwhelming to deal with when we come to plant. All right, we don't get the erosion control for the whole winter, but we are going to protect ourselves against some of that heavy rain in late March and early April. Okay, so we're still going to get some erosion control. It's going to be manageable when we go in, and also what we found is planting green, the planters just seem to work better. Okay. If you go out, burn down early, come back 2 weeks later, unless you're killing it real early. But if you let that stuff bolt and kind of go to head, burn it down, come back 2 weeks later, it just doesn't work.
So you're saying there's additional management here, huh?
Oh, yeah. Always, right? Yeah. Yep. Can't ever just press the easy button. But, yeah, good question there, and I didn't mean to divert into a cover crop talk, but other questions about the sensors, guys? I think I've got a few minutes. Yeah, sure.
Harold mentioned about moisture there. What are the contributing factors in why the yield dropped off opposite direction?
Yeah, so like I said, these soils on the summit here, they're pretty stable. This was a tilled plot that I pulled this transect data from. It's just been tore up. It's rough. There is not much topsoil there. And so when we had all this rain, it was, it just stays wet. We lose a lot of nitrogen. The soil is just not functional there, okay, on the back slope. So that's where our yield decrease comes there. Also, we lost a little bit of stand there. Okay, I should have probably overlaid stand so you could have seen that. It's hard to get a good stand in those clods, basically. Okay, that's what we're planting into. And then at the foot slope, again, it stayed so wet, nitrogen was an issue. Okay, and stand too on some plots because it was just so wet. Good question. Hopefully that's a good thing. Yeah.
So I'm still struggling with your slope by organic matter. So that's sensor organic matter, correct?
Right here?
Yeah.
Or way back in the beginning?
Right there. This way here.
Yeah, this is Smart Firmer OM.
So what's on the left-hand side that we don't see on your slope? Because I'm still struggling why organic matter is going up and topsoil is going down.
Yeah, that's a clay pan uniqueness. Okay? It gets back to, there's a couple hypotheses here. Okay? We don't have a 100% I can tell you the answer to that, but our guess is, my advisor is a soil scientist. He says, okay, part of it's the soil test. Okay, that LOI, there's organic matter that's, that clay, it's got that high amount of surface area. It's just bound in there, and when we burn that off, it's showing up in the test. Okay, the other side of this, we may have a slower breakdown. Okay, because these soils just aren't very functional. Okay, they're really eroded. So when we look at measured, and that's a point that I apologize I didn't show up here, but it actually follows the LOI lab test. So it was doing a good job of predicting OM, but it was not doing a good job of predicting yield potential. So it was doing kind of, in theory, what it's supposed to do. But if we're trying to use that OM to think that's the end-all be-all for yield potential, it falls apart.
So you were using LOI as your lab kind of thing?
Yeah, because that's what they calibrated to. So we wanted to keep it, compare apples to apples there. All right, well, I think we'll call it quits then. Thanks a lot, guys.